Hello, this week we're going to get a start on Chapter 2, which deals with evaluation of job demands. The first question is probably, why are we evaluating a job? It might be a reactive response. You might have had a complaint that this job is hurting my elbow. It might be performance issue that you've decreased the production rate, we're producing less. Why? Or might be performance issue related to quality. We have more errors. We're having more need to rework parts, and so it could be a performance issue. It could be in response to an injury. We've had an employee who sustained a shoulder injury. Is it caused by the job? Okay, so it might be a reactive response, but it could also be proactive, that you're evaluating, assessing jobs across your facility, and so you're just looking at job by job by job as they come before you have any of these other reasons. Okay. So Chapter 2 provides a number of methods that will let you evaluate the job demands, to look at or try to assess the potential risk for injury. Some of them, what type of injury might a worker be more susceptible in performing the job. The approaches will help identify what technique that you want to use to analyze the job. Some of the approaches will be a simple qualitative analysis, and I would say probably almost everybody in this class has done a qualitative ergonomic analysis at some point in their life. In a qualitative, you're collecting basic observational data using tools such as checklists, ergonomic checklists, possibly your JHAs, possibly interviewing workers, possibly looking at the jobs even if you're not collecting data. And so this is more of a qualitative approach. This you often do as you're screening jobs to see if there's a need for further analysis. So we typically start with a qualitative. We might move on to a semi-quantitative if it is a problem job. In the semi-quantitative, you have a mix of observational data, but you also add in some that are easily quantitative. And so, for example, if you're looking at how much force it takes to screw on a lid, you might look at the worker's or employee's face to see, are they grimacing a bit? If so, then that means it's harder, and so we would judge, we would rank, we would assign a numerical ranking to that. And so that's pretty easily quantitative. For the detailed risk analysis, you probably move to the quantitative methods. These provide more objective data. This is we're using measurable quantities. For example, we're going to be looking at biomechanics this week, and so we need to look at forces, we need to look at weights, and so on. And so we need some data that's measurable. Also, whenever you're trying to select the appropriate technique, and again, Chapter 2 provides a number of techniques, another consideration is the time frame to injury. If you break that down into short, moderate, long, short, we expect that as you are put into a job, as you do a job, you can do it once and maybe you'll sustain an injury. And so we're looking at possibly there's some strength data. If the job is too demanding for your strength, you might suffer a sprain, strain, pull, tear, something like that. But this can happen immediately, one time doing it. For moderate sorts of time frames, we're looking at minutes to hours, and on these we're looking at, can you sustain the effort throughout the day? Do you have the endurance to perform the job? Have we provided you enough rest, so enough rest breaks, so we can look at work rest cycles, we can look at job rotation patterns. Okay, so those are your moderate time frame injuries. Well, within ergonomics, for development of musculoskeletal disorders, we can also look at the long-term time frame. These are injuries that takes days, weeks, or years, months or years to develop. So we look at the long-term cumulative wearing out of joints or tissues. And so this week we're going to be looking at biomechanics. That's on the quantitative end of the scale, and it's on the short-term time frame end of the scale. Biomechanics is the study of the human body as governed by the laws of physics. And so we're looking at the application of mechanical principles, such as forces and levers, to the analysis of body posture. And then if you were doing more advanced techniques, we'd be looking at the analysis of body movement. Our objective in applying or using biomechanics is to evaluate the loading on the musculoskeletal system, and I'll often refer to this as stress too. So I'm using stress as a physical quantity, stress as a physical loading on the musculoskeletal system, and we're trying to evaluate it due to its interaction with work. Meaning interaction, the body interacts with tools, with equipment, with machines, and so on. And we're trying to determine, are the tissues within your body, within an employee's body, meaning the structural elements, are they working within safe limits? For example, are we likely to herniate an intervertebral disc by placing too high of a loading on the lower back? So we're looking at tissues working within safe limits, and then we can also use biomechanics to assess if we do make a change, if we lower our workstation, if we change the posture a tool is being used in, if we change the weight of the tool, what are the effects of these changes? Will the changes be enough to reduce the work requirements down into those safe limits? And so since we're looking at forces and levers, we need to review some information from probably from your basic introductory physics class, could be from your trig class also. We're going to start out by looking at a review of forces. If we're talking mass, so we're often told something weighs 10 kilograms, that's really a mass. A kilogram is a mass. So this will be your metric units. If you're looking at the U.S. customary units, this is a slug. So the unit is a slug. Nobody ever talks about slugs. Instead, we always refer to we're lifting 10 pounds or 20 pounds. So there's a little bit of confusion that people think kilograms and pounds are equivalent, but really they're looking at different things. A kilogram is a mass, a pound is a weight. If we want to make them equivalent, then in the metric we would have to refer to newtons, and obviously there would be a conversion factor. But a weight in a metric is a newton, and in the U.S. customary is pounds. If you are given a kilogram, you have to do something to it to make that kilogram a weight. And so if you're given a problem that has a kilogram, a person is picking up 10 kilograms, you've got to multiply that 10 kilograms by gravity by 9.8 meters per second squared to get the number of newtons. And so if it were 10 kilograms, you multiply 10 kilograms times 9.8, that would be 98 newtons. If the problem gives you a pound, a person is lifting 10 pounds. 10 pounds is already a weight. Do not multiply by gravity. The U.S. customary would be 32 feet per second squared. It's do not multiply by gravity if you're given a pound. Okay. So that'll be a little bit of confusion. So just the tip, if you're given a kilogram, multiply it by 9.8 to continue with the biomechanical analysis. Weight. A weight is a force, so we're moving towards forces. Forces, the units are newtons in your metric or pounds in your U.S. customary. So your weight is a force. And so if I weighed 150 pounds, that's a weight, but it's also a force. It's 150 pounds. 150 is the magnitude. But the direction is, well, gravity's pulling me towards Earth, and so the direction of my weight is downward towards the Earth. Okay. Okay, so force is a vector. It has magnitude, so the size of it, the numerical size, but it also has a direction. And so my last question on this slide is I have two lines that are equivalent length, so they're both, for example, 50 pounds. If I'm pulling on a strap, if I pull to the upward right, it's 50 pounds. If I pull to the upward left, it's 50 pounds. The 50s are equal, so the magnitude is equal, but they're pulling in different directions, and so it is not equivalent. Those are different forces. Okay, so magnitude and direction. Since we have a direction, we need to review our coordinate system. We're going to be sticking with a two-dimensional, only doing two-dimensional biomechanics. And so our coordinate system is, we have a horizontal, we have a vertical direction. Our horizontal is our plus x direction. So if a force is pulling to the right, it's a plus x. If it's pulling upwards, it's a plus y. And you would obviously figure out if you have a plus y, you also have a negative y, so downward towards the earth would be a negative y direction. And then if we have a horizontal to the right, we could also have a horizontal to the left, and that would be a negative x direction. Okay, so upward to the right is positive, downward to the left is negative. Okay, so that's our coordinate system. Now for any force that we have, for example, this force going to the upward right, that force can be resolved, meaning broken down into what's known as the x direction of that force. And so if we call that F, the part that goes in the x direction is Fx. The upward part of it is Fy. And so this simple arrow, this F, we can also write it as an Fy, Fx. Those are equivalent. In order to do that, find out if this Fx is 10 pounds, in order to find out how long this is, how many pounds the Fy is, how many pounds the Fx is, we need to go back to our trig, and a quick review of the trig relationship that's necessary to break down forces is this sine-cosine right triangle relationship. And so say we have a right triangle, which means we have a 90-degree angle, so right triangle. This triangle will have a hypotenuse. The hypotenuse is directly across from the 90 degrees, so hypotenuse. I've abbreviated HYP. We have a 90-degree angle, but we have another angle that we would label as theta. The other two sides of this right triangle, we have an opposite side, just meaning that this side is opposite the labeled angle. It's opposite. And we have a side, so a side here that is adjacent to the angle. Okay, so your hypotenuse will be the longest side. You have an opposite side, opposite meaning opposite of the angle that we have labeled. The adjacent is right beside, is adjacent to the angle. Okay. So once we have our basic triangle labeled, we want to look at our trig relationships. The sine of theta is equal to the opposite over the hypotenuse. So sine of theta is equal to opposite over hypotenuse. Cosine of theta is equal to adjacent over hypotenuse. So adjacent over hypotenuse. So knowing any of these two pieces of information, if you know the angle, if you know the hypotenuse, if you know the opposite side, the adjacent side, and by those I mean length, then you can figure out the other two pieces of information. So for example, if we go from our triangle there to, again, another right triangle, opposite of the right triangle is the hypotenuse side, so our hypotenuse is 7 centimeters. We want to find out how long is A and how long is B? Okay, so hypotenuse is 7 centimeters. We're looking for the length of A, the length of B. Knowing that the angle we have labeled is 20 degrees. So this is a 20-degree angle. We use our same relationships that the sine of theta is equal to opposite over hypotenuse. In this case, our opposite side, if we have our angle of being 20 degrees here, our opposite side is A. Okay, so sine of theta is equal to A over our hypotenuse is equal to 7 centimeters. And so rearranging that, if we're trying to find A, we've got sine of theta is equal to A over 7. Theta we know is 20 degrees. And so doing our algebra, taking 7 over here, 7 sine of 20 degrees equals A. We plug 7 times sine of 20 degrees into our calculator, solve for A, and we'll find that A is equal to 2.39 centimeters. Doing similarly for B, for part B, we know that the cosine of theta is equal to the adjacent side over the hypotenuse. And so our cosine of 20 degrees is equal to our adjacent side is B. Our hypotenuse is 7 centimeters. Again, doing our algebra, taking 7 over to the other side. B is equal to 7 times the cosine of 20 degrees. Plug that in our calculator. We should have that B is equal to 6.58 centimeters. Okay, using that same relationship, that same understanding, we now, instead of having the triangle, we just have a force of 11 newtons, meaning that our 11 newtons, it's this long, 11 newtons. We have an angle of 30 degrees from the horizontal. Okay, so this is 30 degrees. We can make our same triangle. Here. We have our x component, we have our y component of that force. And we can see that we can solve for fx, we can solve for fy using that same trig relationship, knowing the hypotenuse is 11 newtons, knowing that our angle is 30 degrees. And so the fx side, fx is adjacent to, is right beside that 30-degree angle. And so fx will be our hypotenuse, 11 newtons, times our cosine of 30 degrees. Plug that into our calculator. We should have 9.53 newtons as being the fx side. So the length of that is 9.53. Fy, knowing that Fy is opposite of 30, of the 30-degree angle, and so that'll be 11 newtons times, in this case we'll use the sine relationship of 30 degrees. In that case it's equal to 5.50 newtons. Okay, so we can break any force if we know what the force is. If you're pulling with 50 pounds, if we know what angle you're pulling at, if it were, for example, 25 degrees, we could find the horizontal component, we could find the vertical component. So we only need to know 2 pieces of information. And so the homework problems will help you practice some of this, resolving forces. The types of forces that we have to worry about acting on the body, or that our body experiences, will be external forces. For example, the gravity pulls a load in our hands. It pulls it downward towards the ground. The loading itself, the object that we have in our hands, it's outside of the body, and so this is called an external force. And that's what we're commonly concerned about is a load the person is trying to lift. Is it 50 pounds? Is it 60 pounds? Is that 100 pounds? We know 100 pounds will be too much. 50 may be okay in certain situations, but that's external. We're used to thinking about that. But we often don't consider our internal forces, and these are the muscle forces acting within the body. As we're trying to hold this 50-pound load in our hands, we know that internally muscles have to be contracting to hold this force. Our muscles also have to be contracting to hold our own body weight in the posture that we assume. Okay. So we have external forces, we have internal forces. An example of an external force would be you've got a couple employees that are trying to move a refrigerator. And so, for example, your employees, Terry and Charlie, they're trying to move a refrigerator. You're looking at a refrigerator from the top. So you have a top view of the refrigerator. You see that Terry walks up to the refrigerator and he or she is pushing at a force of 300 newtons. Okay, so that's the force. And the angle that he's pushing at is 40 degrees from the horizontal. And so this is just like having a triangle like this, a right triangle. You've got a 40 degree. This is 40 degrees. You know the hypotenuse is 300 newtons. And so you could find the X side, you could find the Y side of Terry's force. Similarly, Charlie comes up and helps out because maybe Terry's not able to move it himself. And so Charlie comes up and, well, because they're of their body sizes, they have to separate out and they come in and Charlie pushes at an angle of 25 degrees from the horizontal. So we've got a 25 degree here. And he pushes with a force of 370 newtons in this direction. And so again, we could resolve that into an x component, so cx or cy. And so the question that I'm going to be asking, what is the resultant force of Terry and Charlie in the x direction? That'll be simply tx plus cx. It's moving in, they're pushing in this direction in a negative x direction, so I'll throw in that negative sign there. And so we just go back and resolve each. 300 times you're looking at is tx as a sine or a cosine. You're going to say that tx is adjacent to the angle, so that is a cosine. So 300 cosine of 40 degrees is Terry's part of that. Again, that's a negative direction. We're going to add in, again, negative direction for Charlie. Charlie's cx in that direction is 370, the hypotenuse, times, again, the cx is adjacent, so it's going to be a cosine of 25 degrees. Add those two together. Terry is negative 229.8 newtons. Charlie is 335.3 newtons, and so together it's a 565 newtons. Okay, so you're adding the cx, you're adding the tx, they're combined, this is vector addition, their combined is 565.1, but 565. So if the refrigerator, the weight of the refrigerator plus the friction that has to be overcome as they try to move it, if that total is 400 newtons, 400 newtons is pushing that way against the two employees. So it's a positive. Terry and Charlie together are 565 newtons in the negative direction. You're looking, can they move the refrigerator? Can they move it to the left? And you'll say yes, they can move it to the left because they've overcome the weight of the refrigerator, the friction of the refrigerator, and so it is moving to the left. They are able to move it. Okay, so these two samples are an example of vector addition. At this point, I would like to stop, I guess take a break before we move on to the second part of the lecture.